Wow. Oh, this is so strange. This gotta look weird. It's really cool.
My name is Jason, and I'm that guy rolling around on the floor. I've been a welder and fabricator for the past 20 years. During my career, I have found many tools that I wanted to improve. So I started my own company where I can design better tools. And this is the foundation of every workshop, a table. In my line of work, this table is actually called a fixture table. I've tested the industry's best tables and even prototyped my own, but unfortunately, none of them have met my standards. So today, I'm going to be building, hopefully, the world's best fixture table. So what is a fixture table? Well, it can be described as an elevated work surface with 4 or more stable legs, much like your kitchen table. But that's where the similarities stop. The fixture table's main design is to take many parts and hold them, also arrange them, steady them in a precise location. Now that the parts are held together precisely, the next step is to often glue, fasten, or weld them together. Lastly, it aids in repetition. It's not uncommon to get an order for multiples of the same structure or product, so this helps work quickly and effectively. Oh, and having a table that doesn't catch on fire is a real bonus too.
So this is my very first fixture table, and it's a big piece of plate steel. And this is probably considered the best welding table in the world to most people. But to me, this table is just filled with problems. The first problem you're gonna notice when you're fabricating or welding on a table like this is that you can only clamp around the perimeter of the table, which means hold your parts on the edge. If you have clamps that have a really long throat on them, that's gonna allow you to move your work more inboard. How do you hold your components or parts in the middle of the table? And the solution that most people do is they actually weld the part directly to the table. Just like this custom fixture. There's 1, 2, 3, 4 clamps that are dedicated for this part. And I can't use these clamps for anything else. What a waste of money. But this is what you gotta do when you have a table like this.
Hey, what the hell is this?
Oh, you didn't really give any specific guidelines about
Welding.
The next problem after your fixture's been welded to the table is that you gotta come back and grind the goofy thing off. Not only is that slow, but it leaves the table surface compromised. And the more you do it, the more the table gets ground down, basically eliminating the flatness of your table.
I'm going to be using the word flat quite a bit, and I don't want you to get it confused with level. Level is when the surface is aligned with the Earth's horizon. So with that being said, I can have a surface that's flat, but not level. So let's talk about surface flatness, and it can be described as the highs and the lows of the table surface. And we're going to be using aerospace flatness. You know, the guys that make airplanes and spaceships, they want their tables to be plus or minus 2.5 thousandths in a 2-foot area. So that's our target.
So now we're back to another problem, flatness. This table is not flat because it's a piece of plate steel. Plate steel has a really wide tolerance of how flat it's gonna be coming off the mill, so that's gonna be a problem too. Whatever I weld on top of this dish table is gonna follow that path.
This is the same principle that's applied to building a house. If you start off with a crooked foundation, everything above that is also gonna be crooked.
Originally from the steel mill, somebody has cut this with a torch and it is not square. It's like an 89-degree angle. So I cannot use this surface and this surface as a reference. Not only that, the condition of the edge of this table is rolled because this is a piece of hot rolled plate. That's not even a flat edge to work off of or pull my tape measure from. Because this big huge piece of plate steel is a big problem, people have already come up with a solution, the fixture table. But even those tables aren't perfect, so let me show you.
I've been collecting, studying, and even reviewing these tables for years, scrutinizing every detail and trying to find out which one worked best for me. But there's a lot of problems with them. Problems like, most are the same size as a 4x8 sheet of material, or smaller. Some are too large to reach across. Some have holes that are spaced too far apart, warp or even flex when they should stay rigid. And some of them just aren't even flat. I have really high standards on how I design my tools, so I wanted to fix all these problems with a new table design. Knowing all the problems with the other tables, it's time to create my fixture table wish list. First, I want the table to be a useful size. It'd also be nice to have the table to be thick and heavy duty and built like a tank. It'd also be nice to maximize the surface area. Because I want the table to be really heavy, it's gonna need some strong legs. And I'd like them to be able to elevate the table up and down. It would also be nice to be able to move the table around without using a forklift. And I definitely don't want to weld anything to the table, so some clever way of holding the parts down to the surface would be nice. Since I'll be designing a super table from scratch, we'll need a way to track its capabilities. Much like fantasy football, all the fixture tables that I tested previously, I have ranked in 5 individual categories. We'll look at each table that scored high in that specific category and try to meet or exceed it. But the only way we're going to find out is to actually build the table. So let's get started.
When it comes to building a frame, I have 2 choices. One, like this style, which is a whole bunch of weldments or pieces of tube steel. The second frame style is what I call a platen. And that platen style is basically one big giant piece that's all one unit.
So the main difference between these frames is the amount of parts. My prototype table frame had a bunch of these pieces that all had to be welded together. Anytime something's welded, there's some slight distortion that happens to the frame. In order to remove the distortion and to get the table back into specifications, it generally needs to be machined or milled. The other solution to a welded frame is to, well, just cast the frame. And we call that a platen. Having the frame cast all in one piece is going to keep the parts to a minimum. Plus it makes it easier to assemble. The only table that I reviewed that was entirely cast was the weld cell table, and it exceeded in its frame design, so I'm going to build the table with that platen frame just like that did. Being cast, it also allows me to be more creative in the design decisions later on.
So when it comes to welding table material, we have quite a few options. We have some exotic stuff, like maybe some stainless steel or aluminum, but really, when it comes to practicality, we have 2, cast iron and A36 steel.
By choosing to cast in A36 steel, I know it's abundant and readily available, and it can be made into any size I want. There are a few downsides though. When the table gets scratched, it leaves a nasty burr, and what I mean by that is that the scratched material gets displaced on the surface and leaves a bump, making the table less flat than it was before. Steel can also be subjected to distortion from heat, which is a bad thing if I cast it too thin. And finally, the nemesis of all fixture tables is the weld spatter. Spatter is the byproduct of welding. These little BBs end up sticking to the table. And oh man, do they love to stick to steel. If I choose steel, I'm gonna have to put a coating on it to prevent the spatter from sticking to it. Or, another solution is to just change material altogether. And we can change it to gray cast iron. One of the benefits of cast iron is that it's really hard to weld to. So that makes it a perfect material to make a welding table out of. That way weld spatter doesn't stick to it and makes it easily maintainable. Plus it's bad at conducting heat, which means less heat distortion. That's why you see engine blocks, cylinder heads, brake rotors made out of the stuff. And another benefit is a scratch on the cast iron table will just turn to powder and not displace itself on the surface, so the table can remain flat and require less maintenance. The only table I reviewed that was made from cast iron was the weld cell table, so I know my table can be a platen while still using cast iron material, which is what I'll be going with.
How big should I actually make this welding table? The most common size is 4 feet by 8 feet long.
The problem with the 4x8 table is that my material is the exact same size, so putting it on the table will cover up the entire surface, practically rendering it useless. Why do welding table manufacturers even do this? I find it so frustrating. Even metric tables are slightly undersized from 4x8 and have the exact same problem, so I know I'm going to make my table to be a little bit larger than that. But if I go too large, it will be really difficult for me to reach across it comfortably, so I have found 5 feet to be the maximum width for that reason. As for length, that can really be anything I want, until I run into the problem of transportation and unnecessary cost. As long as it's over 8 feet, that's going to be helpful. The only table that I reviewed that was larger than 4x8 was WeldCell's 5x8 table, which has a wider width but still only 8 feet in length, giving a surface area of 40 square feet. To find the golden size that's not too long and not too short, I'll think I'll oversize my table by 6 inches in both length and width. That's going to give us almost 20% more surface area. That only gives me 38.25 square feet. This still isn't enough surface area. I want more. And the only way to get more is to maximize all the sides of the table. Many tables I reviewed did not make use of all the dimensions of the table by using its sides, including the weld cell. And I think they missed an opportunity. The 5-sided tables that I tested allows me to put tools on the edge of the table, which allows me to extend the table surface, or even put 2 or more tables together to create a mega table.
What do we got here?
Mega desk.
Of course.
On top of that, These sides will improve the table's rigidity. The tables that I reviewed with the most surface area was the Certiflat, which was 48 square feet. So I'm gonna have my sides be at least 8 inches tall, bringing my total surface area to a whopping 55.6 square feet. That ranks this table really high on the usable surface area list. I have a surface now, but I definitely don't want it to just sit on the ground.
We have to talk about table legs, an important component to the table.
There are so many design considerations when considering the function of the legs. At first glance, they just keep the table off the ground, but they do a lot more than that. They can aid in the table's rigidity, keeping the twist out of it. They can also make the table mobile, allowing it to move around the workshop. And finally, its ergonomics can assist the user by being able to adjust the height for comfort, or sitting or standing, or even being able to store something underneath. Not all tables are designed like this though.
This case and this table right here, these legs are height adjustable, which I like, but they're kind of spindly, so the manufacturer has given us braces. They're actually designed to be down here this low. I found that these get in the way if I'm gonna store stuff underneath. If I move these up high, they actually get in the way of me sitting at the table. So naturally, I just took them off completely. There's consequences with that because this table was designed to have the braces around it, and there's only one attachment point up here in this table leg, so I have to be very careful not to shake, rock, or roll this table because I could literally fold the table over on the legs.
And we're gonna have to find a way to attach the legs to the table itself. I want a nice big wide bolt pattern that can really put the leg in a serious side load. This will allow me to not have to put braces on the legs. Where the legs mount is really important. They cannot exceed the outside surface of the table. This is going to allow me to pair two table surfaces together, or marry them, or expand the surface if I want to and not have the legs interfere with each other, while also remaining height adjustable and mobile on wheels. How cool is that? I won't have to worry about the legs folding if they roll over an extension cord or cable around my shop. Now that I know the size and shape of the table, it's now time to focus on making the table straight and strong, and trying to achieve that aerospace flatness. The tables I've tested vary from being super limp and noodly to extremely rigid, with the weld cell and the 5/8 Build Pro deflecting 5/1000ths of an inch. The 28mm Build Pro even got as thin as 4/1000ths of an inch. But I want to surpass these numbers to achieve the aerospace result of 2.5/1000ths of an inch and 2 feet. So how are we going to do it? I'm going to be designing the table with CAD, and this allows me to build the table and test it in a simulation. By adding ribs to the platen, I can test its predicted strength and deflection. Changing the amount of ribs and the height, the thickness, and even the location will all add to the rigidity, and also trying to reduce the cost of manufacturing. CAD also can calculate the weight. I think I ended up around a 3,000 pound platen, but we won't know till we see it in person. I think I ended up with a good balance between weight and rigidity. This sturdy table is no more special than a fancier piece of plate steel, so it's time to give it some utility.
So let's talk about holes for a second.
I can have all my parts on the table, but how will I clamp them down now? A clamp will only work on the edge of the table, so that only leaves me with the perimeter surface. Not only would it be nice to hold my parts down, but I need to arrange my components in a certain way, or whatever the drawings call out for. So some sort of grid pattern would be nice also. I think we can align and hold parts down at the same time. So the way to solve that problem is putting a hole on a grid pattern. And that raises the next question. How many holes do we need? And how often are they? And how far apart are they spaced? So ideally, the more holes I have, the more tooling I can use. If I put too many holes in the table, it could potentially make the surface weaker. Also, there's going to be some spots where it might interfere with the ribbing or the table structure underneath, so we have to avoid that. So 2 inches apart seems like the sweet spot. It's not too wide, not too close, and doesn't interfere with any of the table structure. Now that we know we're going to put a hole, what does that hole look like? Well, we have two choices, and the first one is to thread the hole, so that the table acts like a nut. But there's some problems with that too. The threads offer a place for the grit and grime to hide, and they're always a pain to maintain. Not only the fact that they could get damaged and basically wreck the hole. And then there's cost of manufacturing. 1,756 holes being tapped is expensive, and nobody wants to pay for that. One way to solve this problem is to make a smooth bore hole. We can lock the tooling to the table with the smooth bore hole by creating some sort of binding effect. And once pressure is binding, it's really going to grip the inside of the hole. This makes maintenance a breeze compared to threads. Plus, it's a bit faster to pull the fixture from the smooth hole than have to unthread one.
What size should the holes be in the tabletop? In the current table market, you have two popular sizes, a 5/8 hole or a 28 millimeter. One is really big and one is small. I've found that the 5/8 hole system has some drawbacks. The fixtures are really small and lightweight. The clamps don't have a lot of clamping force, and generally the 5/8 tables are much thinner in size. The first thing I don't like about the 28 millimeter setup is that the hole spacings are too far apart. Generally they're on 4-inch hole spacings or 100 millimeter, and that really doesn't give you enough hole locations to really precision locate your clamps. Also, the fixtures are really long to span those 4-inch hole centers. The fixtures are big and expensive, so I want something right in the middle, and I think we can build that, and that hole diameter for me is going to be 3/4. And when you look at 3/4 is the largest we can fit on a 2-inch grid, and the fixtures are strong enough to be able to take a lot of clamping force. This seems to be the perfect hole size for this table. All the benefits with none of the drawbacks.
The welding table that I tested that had the most number of holes was the Certiflat Fab Block, and that had 1,728 holes. For the Fireball table, its size and grid pattern, it pushes it up to 1,756 holes.
Now that the table's all designed, I want to look at it through augmented reality, or AR, and I'm going to use my phone to do that. This is going to allow me to walk around it, see its size, shape. This looks so strange. I'm smiling from ear to ear. How neat is that? If you guys would like to see this table on your own, I'll leave a link down below so you guys can check it out on your phones also. Here's the small table. I'm going to move it wherever I want to here. I'm going to twist it around. There you go. I'm going to plop it right there, and now I can see the small table. I love the world we live in right now. I'm going to sit at the table. This is going to give me a good perception of where my knees are. Yep. That is so cool.
It's looking great. I think I've checked all the boxes off my wish list, but I'll only know when it arrives. So let's get it made. First, we're going to need a pattern. Usually it's made of wood and is a replica of my CAD model, but with some draft angle added in. That pattern gets pressed into sand. It is then removed, leaving behind a void that the molten metal will fill up. After it cools, the platen is pulled out of the mold and is placed on a gigantic gantry milling machine. This removes all the extra rough material from the surface, bringing it to its final size and flatness. Then after the milling, all 1,756 holes gets drilled on that perfect 2x2 grid pattern. As I wait for the table delivery, I need to make sure the table isn't completely useless. So let's talk about table fixtures, or the tools that go on top of the table.
This is the most important thing on any fixture table system, and that's the tooling. And I think it's the part that most people forget about.
You have to think of this table much like a game of chess. Sure, the board is nice and it keeps the pieces within their boundaries, but it's the chess pieces that perform the specific tasks. In the case of a welding table, the fixtures hold the parts precisely in 3D space. The problem is that I'd like all the pieces to play the game. If I lose one, I can't play. So what if I took these pieces and morphed them into a super piece? One that can perform the tasks of many. That way I'll be able to have less fixtures that end up doing more. This design principle is something I took into CAD in order to create a modular fixture that solves this problem. Now when I get the table back, I'll be able to hold my parts down with precision, but have the pieces do the tasks of many. The topic of fixtures is such a deep rabbit hole that I've made a lot of bonus videos on my other channel that I'd encourage you guys to check out. I would love to go into greater detail, but a truck just pulled up outside with a surprise inside. Look at that!
This thing looks fantastic. Now that it's here, let's see if it holds up to my expectations. So let's run a test. Remember, I'm trying for aerospace tolerance, which is plus or minus 0.02 of an inch in 2 feet. Let's give the table a quick wipe down and we'll throw the straight edge on top and see how flat it is. I'm gonna run this test exactly the way I did in the table review, and then we can compare it to the others that I tested earlier. So here's a 0.002 shim. This cannot slip underneath the straight edge. That's touching, we just go along the straight edge. No, sticky, sticky, sticky. I mean, that's like 2 to 3 thousandths over the entire distance. Let's turn it the other way. Nope, stuck, stuck, tight, tight. So I cannot get a 0.002 shim underneath there. So you can literally pluck a hair out, put it on this table, and I wanna see if the straight edge teeter-totters on it. So what should happen is if I twist this, it should pivot. It's literally pivoting on that 0.002 shim because that's the high spot. Isn't that nuts? This is the most accurate welding table that I have ever measured. I can't believe it's taken me 4 years to get to this point, and this table exceeds all my expectations and then some. I know this table is gonna work perfect for me, and I'm absolutely confident that it's gonna work for you too. There's a big gap in the table market right now, and I know that this table fits right in there. If you want more details, please check out fireballtool.com, and also check out the AR feature. It's really cool seeing this table in your home shop or workplace. So I'm excited to see what you guys create with it. Thank you guys for watching, and I'll see you guys on the next one.